Okay, so it's my pleasure to welcome everyone to this edition of the Órbita webinar. So today we will have Hector Pasten from Universidad Catolica de Chile. So Hector is a Chilean number theorist. So he previously had positions at Harvard University and the Institute for Advanced Studies. He received several awards for his research, including the UMALCA Prize, the Ribenboim Prize, and the MCA Prize. So his work is focused on rational points on algebraic variety, and today he will tell us about Xeric varieties. So please, Hector.
Thanks for the introduction. It's a great pleasure to share my research with you guys. So I hope you enjoy this as much as I did when I was working on this. And I should say, this is joint work with Natalia Garcia-Fritz. We have been thinking about this since 2020. Yeah, I would say 2020. It's been a while. So finally, we wrote out the paper this year and it's posted on the archive. Now, the name is kind of funny, Xeric varieties, and I hope you will agree with me that this is an appropriate name for this kind of varieties. So first, as a motivation, there is Falting's theorem for curves. And in this talk, I will work over number fields. If you don't know what a number field is, you can think about the rational numbers. That's good enough. And there is the theorem of Mordell, the conjecture of Mordell that was later proved by Faltings, that says that if you have a smooth projected curve of genus at least 2, the rational points form a finite set, only finitely many. So for instance, you can take this curve. This is 3 variables, 1 equation, looks like a surface, but this is projective, it's an homogeneous equation. So in fact, this is a curve in the projective plane. And the rational points, sorry, there should be a y here. It's not an x, a y, okay? The rational points of this are exactly the same as the rational solutions up to scaling. And the theorem of Falting says, well, if this curve has genus at least 2, then we're good. It's only finitely many. And in fact, this curve has genus, what is this? Is 4, I think it's 6. I'm not sure, again, probably 6. And that's large enough for the theorem to apply. So you get only finitely many solutions. And in this case, 1, 1, 1 is a solution. Again, this should be, the x here should be a y. Okay, sorry, that's a typo. And there is this definition of Lang, a variety is called Mordelic, after Mordell, if for every number field, the set of rational points is finite. So it's not just for Q, but also for the Gaussians or Q with square root of 2 or whatever number field you have in mind, you want to have a finite set always. And that's the case for curves of genus at least 2. And we want to consider varieties with this property, possibly in higher dimensions. And the question is whether such varieties have a geometric description. Okay, so I look at the variety. Do I need to compute the rational points? Do I need to do arithmetic, or can I just do algebraic geometry and tell immediately if the variety has this Mordelic property? So for instance, for curves, I don't need to go over number fields. I just need to check what the genus is. And if the genus is at least 2, we're good. You get finiteness. But the genus is a geometric invariant. It's not an arithmetic invariant. So in that case, for curves, I do algebraic geometry, and then I get the conclusion about finiteness of rational points. And the question is, can you do something like that in higher dimensions, even conjecturally, okay? And there is, in fact, a conjecture by Green, Griffiths, and Lang. The geometric part is Green, Griffiths, and the arithmetic part is Lang. It should be the case that the following properties are equivalent. First, that your variety is Mordelic. Secondly, that every rational map coming from some abelian variety is constant. Or finally, that the variety is hyperbolic. Yeah, and hyperbolicity for projective smooth varieties means that you have a metric with negative curvature. But for me, it's going to be the condition that holomorphic maps are constant. So for instance, you may remember from your complex calculus class that if you have a curve of genus at least 2, there is the theorem of Picard that says that the holomorphic maps to the curve of genus at least 2 are constant, okay? and that's a hyperbolicity property in the context of curves. Okay, and rational maps from abelian varieties to curves, they are non-constant only when your curve has genus 1 or 0. For genus 2 and higher, rational maps coming from abelian varieties are always constant. So if you don't know what abelian varieties are, they're just algebraic varieties that are projective, smooth. So they are compact, okay, projective, smooth, and they have a group law, okay? They have a group structure, which is automatically commutative because the variety is projective. And this group structure is supposed to be given by algebraic geometry, not just some random group structure. Okay, and the conjecture of Green, Griffiths, and Lang is actually a theorem if you work with subvarieties of abelian varieties. And that's a theorem partially by Faltings, Kawamata, Bueno, Green, Bloch, and plenty of other people that work on this sequentially, and eventually it led to this full statement. Okay, all results in the literature for this Green-Griffith-Lang conjecture, including the modelicity. So all the results that have to do with arithmetic, they come either from the case of abelian varieties done by Faltings, or from the Chafarevich conjecture, also due to Faltings. Okay, and we kind of ran out of tools. That's basically what we know how to do, and that's it. Okay. Okay, here's a math challenge. I like this exercise very much. I found this on Facebook some years ago. And if you are an expert on Facebook experiments and exercises, you will notice that this apple is a whole apple. So it's not half an apple. So these fruits are supposed to be positive integers. Okay. And the question is, can you find these three positive integers, the number of apples, the number of bananas, the number of pineapples, the three positive integers, so that you plug them in this equation and you get 4. That's a challenge, okay? And you try for a bit, and it says 95% of people cannot do this. And if you can do this, you are in the higher 5% of people, the smarter guys. And well, I tried and I failed. So I was not in the top 5%. But there is a good reason why I failed, is that the equation is this. If you don't like fruits, you put variables, and this is the equation. And I don't know if you can see a solution, but I could not. And the smallest solution is this. This is x. This is just one number. It didn't fit in one line, okay? This is x, this is y, and this is z. This is the smallest solution of the equation, okay? And if you look for solutions for a while, you will not find this, okay? And in fact, there are infinitely many solutions. It's just that they are just too big. They are very sparse. You find the first one, and then you search for years, and you don't find the next one until eventually you find it, and then search for more years and keep going. Okay. I mean, years if you do it by hand. Okay. If you do it on a computer in a smart way, then you can find this in a quicker way. And the problem, the equation, if you manipulate the equation, eventually you get an elliptic curve, okay? An elliptic curve, a curve of degree 3. And this elliptic curve happens to have positive rank, meaning that it has infinitely many solutions. And then it's a matter of finding a solution whose coordinates are all positive, and you try for a while iterating the solution, and you find the first one, and you get these numbers, okay? So it's quite surprising that this funny looking exercise, you know, the numbers here are very small. The largest number in this equation is 4, and nonetheless leads to these huge solutions. And it's not that this is one solution. This is the smallest solution. There is nothing smaller solving the equation, okay? And in fact, this exercise came from a paper by Brennan and MacLeod. And this paper explores all their equations that are surprisingly hard to solve, but nonetheless, they have infinitely many solutions. Why am I mentioning this? Because this is not Mordelic. This is not a situation where you have only finitely many solutions. You have infinitely many. They're just hard to find, okay? So you have the situation where you have many solutions and they are abundant. You find them all the time. Like, for instance, the Pythagorean equation, the smallest solution is 3, 4, 5, and you take 3 squared plus 4 squared equals 5 squared. That's a solution. And there are plenty of other small solutions, and keep going and you find more. So that's one case. The other case is that you have infinitely many solutions, but they are really difficult to find, like here. And the other case is that you don't have infinitely many solutions. There are only finitely many. So you can consider these three situations. And the two extreme cases are very well studied when you have many solutions and when you have finitely many. There is a lot of attention put onto this. But the middle case has not been explored too much. And that's where I want to put my attention. You have infinitely many solutions, or maybe finitely many, but they are difficult to find, okay? Here. So that's the moral of the story, that finiteness is very important, but you may have infinitely many, but if they are hard to find, in practice, the equation looks like it doesn't have solutions. Okay, now when you have a projective variety and an ample line bundle, if you don't know what an ample line bundle is, think about equations. You choose equations for your variety, okay? Attached to this, there is a height function, and the height function measures the complexity of the solutions. For instance, if you're working with rational numbers, the height function is the largest of the numerators or the denominators of your coordinates. So it measures how complicated it is to write down your solution. And this height function, it's given to you if you choose the ample line bundle. And when you have an open set in your variety, or if you want the full variety, that's fine also, you count how many points you have up to that height. For instance, how many rational numbers you have up to height 1? Well, you have 0, 1, minus 1. You have 3. Up to height 2, you have 0, 1, minus 1. 2, half, minus 2, minus half. So you have a few more and keep going, okay? For height 3, you get something else. For height 3, you get 3 over 2, for instance, okay? So you count how many points you have in your variety, how many solutions your equations have up to certain height. And there is a property called the Northcote property telling you that this is going to be finite, so you can actually count, which is quite natural over the rational numbers. If you bound the numerator and the denominator, then you have only finitely many fractions, okay? So that over the rational numbers is quite natural. Okay, so for instance, if you have a smooth projective curve of genus G, for genus 0, this is like counting points in the line or counting points of the solutions of the Pythagorean equation. That's a p-adic, and that grows like a power of the variable, okay? It could be linear, quadratic, or square root. It depends very much on what is the line bundle you're using. But it grows like a power of the bound. For genus 1, you have elliptic curves. And elliptic curves have this property that coordinates of their solutions grow fast. And how fast? Like exponentially. So when you count solutions up to certain height, you only get a power of logarithm. So this grows slower. And the other case is genus at least 2, in which case you have only finitely many solutions, and this counting function remains bounded. So that's the three behaviors for curves. There is nothing in the middle, nothing. Like, for instance, you may wonder about a curve having log, log, log number of points up to a bound that does not exist. It's either constant or power of logarithm or power of the bound. That's it, okay? So definition, you have a variety and you want to count points. And suppose that up to certain height, the number of points grows smaller than any power of the variable. Could be logarithmic, could be power of logarithm, could be, I don't know, something smaller. I mean, it doesn't need to be logarithmic, but as long as it grows slower than any power, that's the situation I want to consider. And in that case, I will say that the points are sparse. They are hard to find. You go up to a bound and you have very few of them, okay? And you can quantify this with the counting function. And the variety is going to be Xeric if you get a sparse set of points over any number field, not just Q, over any quadratic extension, cubic extension, degree 4 extension. It doesn't matter what the number field is. If you always get a sparse set of points, if the counting function is always slow, then you say the variety is Xeric. Okay, so for instance, for curves, let me go back here. Curves are not Xeric because you grow like a power of the variable. But genus 1 are Xeric because it grows like a logarithm to some power. So that's smaller than t to the epsilon. And genus at least 2, they are also Xeric because they grow like t to the power 0, okay, which is constant. And the terminology being Xeric comes from biology. And okay, so these are some pictures from my country, Selva Valdiviana. This is in the south of Chile. And this is not a Xeric biome because there is abundant vegetation. There is plenty of vegetation and trees and water, and it's very, very good for life, okay? But then there is Pampa del Tamarugal. This is in the center north of Chile. And this biome, in biology, they call it Xeric. And that means, from Greek, it means very dry, okay? And it does have vegetation. It's not that it doesn't have, it does have, but it's sparse, okay? This is a picture of Pampa del Tamarugal. And then there is also the Atacama Desert, and this is in the north of Chile, and this is also Xeric because there is no vegetation at all, okay? So it's also very dry, and therefore that's a problem for vegetation. So these two situations are, I want to think about this as, this is like genus 2 curves because you don't have the rational points, or you have only finitely many. This is like genus 1, you have rational points, but they are sparse. And this is plenty of rational points, like genus 0, okay? So there is a silly reason for a variety to be non-Xeric. We already saw that rational curves, genus 0 curves, they have plenty of rational points. So if your variety contains a rational curve, then it will contain plenty of rational points, okay? And the conjecture implied by a conjecture of Manning is not exactly Manning's conjecture, but it will follow from Manning's conjecture. The conjecture is that that's it, okay? The conjecture is that if your variety does not contain rational curves, then it is going to be Xeric. And if it contains rational curves, it's not Xeric. It's an if and only if. One direction is trivial, is the other direction that's part of the conjecture, okay? So the question is, can you tell Xericity just from the existence or non-existence of rational curves, okay? Curves of genus 0. And I insist, curves of genus 0 are in this situation. So trivially, the number of points is too many points, okay? They grow like a power of the bound. There is a question? No? Okay. And there is a theorem of David McKinnon that says that Voita's conjectures and the conjectures of the minimal model program, namely that you have plenty of rational curves if your variety has negative codimension, these conjectures imply the previous conjecture, okay? So it's like conjecture A implies conjecture B. I don't like that. It's like having no theorem at all. But nonetheless, it's some motivation for this conjecture of Xericity, trying to identify when a variety is Xeric. And I insist, Xeric is not just rational points are sparse. Is that rational points are sparse over every number field. Okay, it's a property that's possibly geometric because it does not depend on the particular number field you're working with. It's supposed to be preserved under extensions, okay? So maybe the conjecture is true, but of course you want to prove it, not just having this fantasy mathematics when you have one conjecture implying the other conjecture. Okay, so the conjecture I mentioned in the previous slide relates arithmetic and algebraic geometry. Okay, rational curves, genus 0 curves, that's algebraic geometry. Xericity is arithmetic. But the Green-Griffiths-Lang conjecture had another component, which is hyperbolicity, complex analysis. Okay, what about Xeric varieties? Can I expect a conjecture saying something like, you have this property about complex analysis, and then you are Xeric? Can I have something like that? I don't know, but you have something else. There is this conjecture of William Cherry that says that if you have a smooth projective variety over the p-adics, okay, this is the complex p-adic numbers, okay, then the variety contains a rational curve if and only if there is a p-adic analytic map to the variety that's not constant. Okay. So just to clarify, this is different from the complex case. In the complex case, you have the Weierstrass P function going to elliptic curves. In the p-adic case, there is nothing like that. Okay. From the affine line, every map to an elliptic curve is constant. Okay. That's in the p-adic world. And that's consistent with the fact that you cannot have a rational curve mapping to an elliptic curve. Genus 0 cannot go to genus 1, non-constantly. So going back to this conjecture of Cherry, it's over the p-adics, it's not over number fields. If you want to say something like this over number fields, like I want to do, you need to do an argument, okay? It's not for free coming from this transcendental setting. Okay, so there is some classical progress. Berkovich did the case of curves, that genus at least one are p-adic hyperbolic, to so say. William Cherry did the case of abelian varieties. And let me put all together with some work, as I said, because the conjecture of Cherry is transcendental. I want to do something arithmetic here. So the main conjecture I want to discuss is, take a smooth projective variety over your number field K. Think about the rational numbers. Then the following are equivalent. First, the variety is Xeric, meaning that over every number field, you have only a sparse set of rational points. Secondly, the variety contains no rational curve geometrically. Okay. And then for some prime, there is going to be a non-constant p-adic analytic map to the variety. And then for every prime, that happens. So Xeric should be like p-adic hyperbolic, okay, p-adic hyperbolic, either for one prime or for all of the primes, or whatever in the middle, okay? So the conjecture is that if you have p-adic hyperbolicity for one prime in this setting, then you have it for all of them, because this should imply Xeric, and Xeric should imply p-adic hyperbolicity always. Okay, this is the conjecture. And okay, so this conjecture follows some other conjectures, and that's not the end of the talk, because I think that's kind of fantasy math. Of course, there are conjectures that are better accepted, but I don't know. I mean, you want to have a theorem, right? So a useful fact that I'm going to use a few times is that the main conjecture is compatible with étale covers. So if you have a variety and you have an étale cover and ramified cover, then you can prove your conjecture upstairs or downstairs and implies the other case. Okay, that yeah. So this is not for free. You need to do some little work here. For instance, in the arithmetic case, you need to argue by Chevalier-Weil. Okay, that's a theorem about preserving mapping points. Okay. Under étale covers. So there is some work to be done here. It's not something for free, but you do it and you get this compatibility for étale covers. Okay. Right. What do you get out of this lemma? So fine, you have compatibility with étale covers. What can you get? Well, you get some stuff. Here I want to mention what do I mean by this, but I think I already explained that. I will not stop with the p-adic case, okay? So some special sets, the set of rational curves, okay? And then you take Zariski closure. The set of p-adic analytic maps, and then you take Zariski closure of the image. Non-constant p-adic analytic maps, okay? And naturally, rational curves are examples of p-adic analytic maps, so you have an inclusion. And the question is, do you have equality always? And I put this as a question because I have no intuition whether this should have a positive or negative answer. I just want to state this as a problem, an open problem, and it's up to you guys to prove it or show it's wrong, okay? Fine, so the conjecture is that in this setting, the conjecture is that if you delete the statistic closure of the rational curves, that's the largest open Xeric subset of your variety. And one can, it's not immediately clear, but you can use McKinnon's work to show that this will follow from Boyta's conjecture and the minimal mobile problem, okay? There is some variation of the argument. All right. Good. So the main conjecture is true for abelian varieties. Maybe I should go back to the main conjecture and check this is correct. Okay. So abelian varieties, are they Xeric? Yes, because abelian varieties have this group law and the height grows exponentially, and therefore the counting of points is power of logarithm. So yes, the abelian varieties are Xeric. Okay. Then abelian varieties do not contain rational curves. That's a well-known theorem. And then by Cherry's theorem, Cherry says that abelian varieties are p-adically hyperbolic. So yes, for abelian varieties, everything holds. Okay. Now here is a less obvious case. You consider varieties with Neff tangent bundle. Abelian varieties are an example because abelian varieties have trivial tangent bundle, but more in generality, you may wonder about varieties with Neff tangent bundle, and the conjecture holds in this case, in more generality. But this is kind of a tricky argument where you don't prove a lot. Okay, you'll see. So there is a theorem of classification that says that up to an étale cover, these varieties with Neff tangent bundle are nothing but fibrations over abelian varieties, and the fibers are Fano. Okay. So you have two situations. The fibers are positive dimensional. If the fibers are positive dimensional and Fano, you can invoke a very deep theorem of Mori saying that they will contain rational curves. Okay. And then you map your rational curve, and then you destroy all the properties. So the variety will not be Xeric, it contains rational curves, and therefore it contains p-adic analytic maps. Okay. And then you prove your theorem because everything is false. And false is equivalent to false, and the conjecture is that the three properties are equivalent to each other. Okay. Now, what if the fibers of this fibration are zero-dimensional, meaning, well, up to an étale cover, you have an abelian variety. But I already explained that for abelian varieties, the conjecture is true. And I already mentioned that the conjecture is stable under étale covers. So you get the conjecture in the positive way for these varieties when the fibers are zero-dimensional. So you see that we didn't prove a lot. It's just compatibility and then deducing from previous theorems. Okay, but this is an example of a large class of varieties where that goes beyond abelian varieties, where you have the conjecture. So, and this is a theorem; it's not conjectural. Okay. So when the cotangent bundle, so this was for the tangent bundle being positive, or at least not too negative. And now, what if you have positivity of the cotangent bundle? When the cotangent bundle is Neff, the variety contains no rational curves. This is a well-known argument. So the main conjecture suggests that if you have Neff cotangent bundle, like weakly positive, the variety is going to be Xeric, and there is no p-adic analytic maps that are non-constant. So it's p-adic hyperbolic, under the assumption that the cotangent bundle is Neff. Well, the first one, you need to work a little bit, but the first one will follow from conjecture of Voigt. Now, going back to the case of complex numbers, there is this theorem of Kobayashi saying that if the cotangent bundle is very positive, meaning ample, okay, then the variety is hyperbolic. Every complex analytic map is constant. For p-adics, I want something like that, but with very weak positivity condition, Neff only. And that should be enough to say that the p-adic, the variety is p-adically hyperbolic. So that's kind of funny that you ask for much less in the p-adic world. Okay, and we can prove something, but in the middle, okay? Semi-ample. Semi-ample means, okay, fine, maybe it's not ample, but at least some symmetric power will be globally generated. Okay. So the semi-ample condition is kind of in the middle between Neff and ample. And we can prove that if the cotangent bundle is semi-ample, then the variety is p-adically hyperbolic. Okay. Yeah, this is what I mentioned. Semi-ample lies in the middle. Okay. Another situation when you can prove things is when the fundamental group is large. Okay. So the algebraic fundamental group classifies étale covers. And there is this definition of Jan Scholar saying that if you have a smooth projective variety over the complex numbers, you say that the fundamental group is large if for every positive dimensional subvariety, the map at the level of fundamental groups has infinite image. So for instance, in this situation, the variety cannot contain rational curves because the fundamental group of a genus zero curve is trivial. Okay, so in particular, the image is finite. And be careful that I need to work with the desingularization, which is always available sorry, where is it? Okay, it's always available by the, what is this thing? I forgot the name. You know what I'm talking about.
Hironaka.
Hironaka, thank you very much. Yeah, Hironaka. Thanks a lot. Yeah. And by Hironaka's theorem in characteristic 0, because in characteristic P we don't know this, but in characteristic 0 you have the singularization, so it makes sense to have this definition. Okay, so if you have a curve, the fundamental group is large if and only if the genus is at least 1. Okay, the positive dimensional varieties are the curve itself. That's it. You don't have a lot to check. Abelian varieties, this is not obvious, but it's true that abelian varieties have large fundamental group in this sense. Compact ball quotients, like fake projected planes. So these guys are hyperbolic, but at the level of fundamental groups, they have large fundamental group. Again, this is not obvious, but it's something that people already know. Okay, and this is interesting because abelian varieties are not hyperbolic. Compact ball quotients are hyperbolic, so this is not really detecting hyperbolicity. This is doing something else. And there is this interesting theorem, very beautiful theorem, kind of recent, that says that if you have a smooth projective variety with large fundamental group over the complex numbers, okay, I read this wrong. Okay, the variety is defined over a number field. The condition of fundamental group being large, you need to check it over the complex numbers. Okay, this is what I mean. In that situation, the variety is Xeric. Over any number field, the counting function of rational points grows very slowly. So the rational points are sparse over every number field. And the idea is the following. Using largeness, you construct étale covers because the fundamental group classifies étale covers with the property that the positive dimensional subvarieties have large degree. Okay, the degree is bounded from below. And then projective varieties of large degree usually have slowly growing counting functions. Think about this. If you have a line in the plane and you count, think about integral points just to make it easier, okay? Integral points in the line, if you count them by size, the counting function is linear. But if you have a parabola, the counting function grows slower, like square root, okay? So the higher the degree, the fewer points you see on a box. And then you go to the limit because the fundamental group is large. So we're talking about infinite fundamental groups here. So you go to the limit and then you can prove in this way that the rational points are, the counting function has exponent epsilon for every epsilon. That's basically the idea. Of course, there are many details that go into the proof. And as a corollary, compact ball quotients for compact Borel quotient, the main conjecture is true. How is this? Well, let me explain. They are Xeric by the previous result. The cotangent bundle is ample because, well, there are quotients of a symmetric domain, and the cotangent bundle is going to be ample. And in particular, is semi-ample. And by the theorem we proved before, the semi-ample cotangent bundle implies that it's p-adically hyperbolic. So don't get me wrong. These varieties, these compact Borel quotients, are complex hyperbolic. We do not know whether complex hyperbolicity in general implies p-adic hyperbolicity. There is something else going on here. They are complex hyperbolic, but the reason is that the cotangent bundle is ample. And that's the information I'm using, okay? Okay, what if we don't assume that the fundamental groups are large? Well, you can still get something like if you have positive irregularity, if you have differential forms. In the case of a surface of general type, if you have differential forms, this is kind of a long statement, but the moral of the story is that if you have differential forms, there is going to be an open set that's Xeric. Okay, there is some little assumption here in the case of irregularity 1. Maybe I should explain where this assumption is coming from. Irregularity 1 meaning that you have one differential form up to scaling. Oh, there is a little hat here. It means that you need to check differential forms up to étale cover. And that's what it says, okay? So up to an étale cover, the Albanese map goes to an elliptic curve. This is something general about the irregularity. And you have a vibration, like in this picture, okay? Yeah, well, there is some jabba you need to do, like taking factorizations, time factorization, and things like that. But at the end, you get some vibration, okay? And the fibers have genus at least 2 because I'm assuming that my surface is of general type. I want to count points of bounded height fiber by fiber. There is this theorem by Dimitrov, Gao, and Habiger that says that the total number of points in the fiber is finite. We knew that, but not only finite, you can bound the number like a power of the rank of the Jacobian. Very uniformly, okay? So instead of counting points on the fiber up to a certain height, I count all of them. And we are lucky enough that this bound for the number of rational points, all of them, is very well controlled, is rather uniform. People say this bound is uniform. It's not uniform, okay? Depends on the rank. So you need to control the rank now. So you add over points on the base of bounded height and the assumption of class groups. Or if you don't want to make an assumption of class groups, just make the assumption that the ranks of abelian varieties do not grow very fast, okay? Some people believe that they are even bounded. So yeah. And in some cases, if your curve gives you a Jacobian with rational torsion, then you can actually prove something like this, that the rank grows slowly. At any rate, the assumption on the rank allows you to control, well, this part of the bound, and then you put everything together. Quite importantly, on the base, the rational points are sparse because this is an elliptic curve. So you put sparse Cartesian product finite, and things grow slowly, so you get sparsity over the surface, okay? So that explains, I guess, the first case. The second case is much easier, so I will not say anything here. Now, there is another invariant, the S invariant of the diagonal. What is this thing? It's some positivity measure, okay? You take the diagonal of x times x. X is some variety, okay? Whatever variety you want to take. You take the diagonal and you ask yourself, well, how many times can I subtract the variety, the diagonal from this ample line bundle? How many times can I subtract the diagonal so that it remains nef? Okay. So here's an example. You take P1 cross P1, the line cross the line, okay? And you take your ample line bundle a point. Your ample divisor is a point. So this A cross A is going to be a line, cross a line union a line, okay? Vertical line union a horizontal line. That's your divisor. The diagonal is linearly equivalent to the same, to a line union a line, okay? That's a diagonal in P1 cross P1, not in every curve, but in P1 cross P1, that's the case. And if you subtract one from the other, you get linearly equivalent to 0. That's NEF, and that's the best you can do. So in that case, this invariant is going to be 1, okay? It's going to be 1. So the S invariant for the diagonal in this situation of P1 cross P1, for the divisor A equal a point, and then you get 1, okay? Just to clarify what this is measuring. Some remarks, well, it's kind of trivial, but this is never 0. It's going to be positive, okay? And this is the reciprocal of a Széchenyi constant, in case you are familiar with Széchenyi constants. There is this really beautiful theorem by Tanimoto saying that this geometric invariant controls arithmetic. The counting function of rational points is bounded by the bound to the power the S invariant. Okay. Now, this is not enough to show something is Xeric because this S invariant is never 0. But nonetheless, you get a bound. Okay. And well, the proof is really beautiful. The proof says, well, the diagonal is positive. Therefore, there is some repulsion of rational points. And since the rational points repel each other, on a ball, you cannot have too many of them. And that's basically the idea of how you show that the points are sparse. Okay, this is what I just said. And let me define the S hat invariant. The S hat invariant is the S invariant, okay? But up to étale covers. Up to étale covers. And you may say, well, this is just small variation. Things should be kind of the same. Sure, they are the same. There is some argument to do because, yeah, it's not immediately clear what is the relation over étale covers. You need to work here because rational points lift, but the counting functions, you need control on them, okay? Remember, I mentioned before that the main conjecture is stable under étale covers. That's fine because the exponents were epsilon, but here the exponents are not epsilon. There are some well-defined, uniquely defined numbers. And you want to keep those numbers when you go to the étale cover, and that requires some work. It's not immediately clear. Okay, whatever. So at the end, you get that the number of rational points can be bounded by a power, and the power has the S hat invariant. Okay. And you may say, well, this is just small variation, but no, there is something going on here. And what happens is that the S hat invariant can be 0. It can actually take the value 0. So this S hat invariant, yes, you can use this one to show that variety is Xeric. And for instance, and this is the corollary, okay? For instance, abelian varieties have S invariant equal to 0. Compact ball quotients have S invariant equal to 0. So we get different proofs of xericity for these two kinds of varieties. Okay, independent of the previous argument I mentioned regarding the degree of the varieties and the large fundamental group. So this proof has nothing to do with large fundamental groups. And conjecturally, the S invariant, the S hat invariant is going to be 0 for all varieties with large fundamental group. So possibly this theorem is more general, but of course one has to prove this geometric conjecture. Yeah, some questions. I want to finish the talk with some questions. For modelicity, like, yeah, for finiteness of rational points, we don't know what to do in a lot of generality. We only have subvarieties of abelian varieties or the Chafarevich conjecture. That's basically what we can do for modelicity, finiteness of rational points. For being Xeric, we can do much more. For sparsity of rational points, we can do much more. Basically, this talk was a selection of techniques that I want to share for trying to show that something is Xeric, okay? But if you look carefully, every technique I mentioned today needs that the fundamental group is infinite. Okay, it could be torsion, fine, but infinite. Question: can you prove at least one example of positive dimension of a variety that's Xeric, like sparsity of rational points, but the fundamental group is finite? I have no idea how to do this. I don't know a single example. So that would be very interesting, at least to me. Okay. And Cherry conjecture that there is no p-adic analytic map to a K3 surface. But let me make the conjecture more general. If you have a p-adic analytic map to a variety having Zariski dense image, then I forgot to mention Zariski dense image here in Cherry's conjecture for K3s. Okay. So if your p-adic analytic map has Zariski dense image, then the codiary dimension has to be negative. That's a conjecture. Okay. This is very different from the complex case. In the complex case, if you have a holomorphic map with Zariski dense image, then it could be whatever. I mean, I guess that conjecturally will not be general type, but other than this, there are examples that could happen. So yeah, so it's nothing like this in the case of the complex numbers. I gave this talk in 2023, long before the paper was written, and Daniel Lead asked this. Well, suppose the Zariski dense image hypothesis for some p-adic analytic map. Question: is the variety unirational or maybe uniroofed? So under the minimal model program, these two properties are quite related to negative codiary dimension, but as far as we know, there are different conditions up to today. Okay. So this is a different take on the problem. And thanks for your attention.
Thank you very much, Hector, for this very beautiful talk. Maybe let me ask here in the Zoom if there are some questions. I don't see anything in the
This
chat.
is not a question, but I love your pictures, Xeric.
Thank you.
It was a very clear lecture. I enjoyed it a lot.
Thanks.
Maybe I have a few questions. So I don't have much much intuition into this p-adic hyperbolicity. So let me ask you something. You mentioned, so you had these three conditions in the conjecture, in the main conjecture. And then you mentioned that one direction, at least two of the conditions will easily imply the non-existence of rational curves. But if you want to compare the Xeric condition with the p-adic hyperbolic, so is it, how would you say?
I have no idea how to do it.
But I mean, is there one direction that you expect to be? Okay.
Okay, I expect they are equivalent, of course, but
No, but that there is a direction that is easier to prove than the other?
there is one direction that's hard and the other direction is impossible. The hard direction is that if you have a p-adic analytic map, then mod p, you have a rational curve, okay? And then you can try to lift this rational curve to characteristic 0. And if you manage to do that, and there is a big if here, but if you manage to lift this rational curve to characteristic 0, the rational curve will carry a lot of rational points. So it will not be Xeric. So that's a strategy, but at least give some intuition why the p-adic assumption being false implies the Xeric assumption being false. Okay. But the other way around, I have no idea how to do something like that.
Okay, and then actually another question. When you mentioned the conjectures from the MMP, so which conjectures are you talking about exactly? The abundance or?
Well, abundance is necessary for this thing, but there is also this negative codiary dimension implying that you have plenty of rational curves.
Okay.
Yeah.
Okay, and then maybe just one comment that I am actually surprised that 5% of the people got to write the Facebook challenge. So I don't.
I guess, yeah, I guess that depends what is the group of people, right?
Okay. Maybe
You
yes.
ask 20 people, one of them created the question, then fine.
It is not said that 5 people know. It said that 95 cannot. Maybe it's
That's
more
right.
than 95.
That's right. That's
Okay,
right.
that's true. That's correct. Okay, so let me see. Are there more questions for Hector? No? Well, in this case, Hector, thank you so much again for this was a very beautiful talk.
Thanks.
And I guess now we take a break and then we resume the Órbita webinars in the beginning of 2026. And I guess everyone will hear more about this soon. Okay. Bye-bye.
Bye.
Bye, thank you.